Reversible Addition Fragmentation Chain Transfer, RAFT, Polymerization, Mechanism, Control, and Recent Developments. Reversible Addition Fragmentation Chain Transfer, RAFT, Polymerization is one of the most versatile techniques within the class of Reversible Deactivation Radical Polymerization, RDRP. It enables the synthesis of polymers with controlled molecular weight, narrow molecular weight distribution, and well-defined architectures while retaining the broad monomer compatibility typical of conventional radical polymerization. Since its discovery in 1998 by researchers at the Commonwealth Scientific and Industrial Research Organization, CSIRO, RAFT polymerization has become a widely adopted method for producing functional polymers, block copolymers, and complex macromolecular structures. This video summarizes the principles of RAFT polymerization, describes its step-by-step reaction mechanism, discusses the role of RAFT agents and monomer types, and highlights recent advancements that expand its applications in materials science, nanotechnology, and biomedical engineering. Controlled or living radical polymerization techniques were developed to overcome the limitations of conventional free radical polymerization, which typically produces polymers with broad molecular weight distributions and limited architectural control. RAFT polymerization is one of the most successful approaches for achieving controlled radical polymerization while maintaining the versatility of radical processes. The technique was first reported in 1998 by researchers at the Commonwealth Scientific and Industrial Research Organization in Australia. Since then, RAFT polymerization has evolved into a powerful synthetic tool for designing advanced polymer architectures, including block copolymers, star polymers, polymer brushes, and gradient polymers. RAFT polymerization maintains control over polymer growth via a reversible chain transfer process mediated by thiocarbonyl thiol compounds, commonly known as RAFT agents. These compounds regulate radical activity through a dynamic equilibrium between active propagating radicals and dormant polymer chains. Fundamental principles of RAFT polymerization. RAFT polymerization is a member of the family of reversible deactivation radical polymerization, RDRP, methods, alongside techniques such as atom transfer radical polymerization, ATRP, and nitroxide-mediated polymerization, NMP. The defining feature of RAFT polymerization is the presence of a chain transfer agent, CTA, containing a thiocarbonyl thiol group. The RAFT agent mediates polymerization via reversible addition fragmentation reactions that maintain an equilibrium between active radicals and dormant polymer chains. Key characteristics of RAFT polymerization include controlled molecular weight growth, narrow molecular weight distribution, low dispersity, compatibility with many vinyl monomers, tolerance of functional groups such as O, COOH, NR2, and SO3H. Applicability in bulk, solution, emulsion, or aqueous polymerization systems. Because most polymer chains remain dormant during the reaction, termination reactions are significantly reduced, enabling features resembling living polymerization. Step-by-step reaction mechanism of RAFT polymerization. The RAFT process operates in conjunction with the standard steps of free radical polymerization, initiation, propagation, and termination. However, additional reversible chain transfer reactions regulate the activity of growing polymer chains. Step 1. Initiation. A radical initiator, I, decomposes to generate free radicals. These radicals react with monomer molecules, M, to form propagating radical chains. The resulting radical species initiates polymer chain growth through successive monomer additions. Step 2. Addition to the RAFT agent. The propagating radical, PN, reacts with the thiocarbonyl double bond of the RAFT agent. This step forms a radical intermediate containing the thiocarbonyl thiol group. Step 3. Fragmentation and radical release. The intermediate radical undergoes fragmentation, producing a dormant polymer chain containing the thiocarbonyl thiol group, a new radical species, R. The newly generated radical, R, can initiate polymerization of additional monomers. Step 4. Reinitiation and propagation. The released radical reacts with monomers to produce a new propagating chain. This ensures that many polymer chains begin growing at approximately the same time. Step 5. Reversible chain transfer equilibrium. The propagating radicals, PN, and PM, repeatedly undergo reversible addition fragmentation reactions with the RAFT agent or dormant polymer chains. This rapid equilibrium ensures that most chains remain dormant while only a small fraction are actively propagating at any given time. Step 6. Termination. As in conventional radical polymerization, termination may occur through radical coupling or disproportionation. However, the RAFT equilibrium greatly reduces the concentration of active radicals, minimizing termination events. Role of RAFT agent structure. The performance of RAFT polymerization strongly depends on the structure of the chain transfer agent, particularly the Z group and R group. Z group. The Z group regulates the reactivity of the C=S bond and stabilizes the intermediate radical. It influences the rate of addition and fragmentation during the RAFT equilibrium. R group. The R group acts as a leaving group during fragmentation. It must readily dissociate from the intermediate radical, efficiently reinitiate polymerization. Proper selection of the R group ensures rapid exchange between active and dormant chains. Common classes of RAFT agents include dithioesters, trithiocarbonates, dithiocarbamates, and xanthates. Polymerization of different monomer types. RAFT polymerization can be used to polymerize a wide range of vinyl monomers. More activated monomers, MAMs. These include styrenes, meth, acrylates, meth, acrylamides, acrylonitrile, and vinyl pyridines. For these monomers, aromatic dithioesters and trithiocarbonates are commonly used RAFT agents because they stabilize the intermediate radical effectively. Less activated monomers, LAMs. Examples include vinyl acetate and N-vinyl amides. For LAM polymerization, xanthates and dithiocarbamates are preferred RAFT agents. These groups reduce the stability of the intermediate radical and facilitate faster fragmentation. Polymer architectures accessible by RAFT. Because the thiocarbonyl Thio group remains attached to the polymer chain end, the resulting polymers can function as macro chain transfer agents, allowing sequential polymerization of additional monomers. This feature enables the synthesis of complex macromolecular structures, such as block copolymers, gradient copolymers, star polymers, polymer brushes, microgols, and functional nanomaterials. Recent advancements in RAFT polymerization. In recent years, significant advances have expanded the versatility and applications of RAFT polymerization. Photo-RAFT polymerization. Light-mediated RAFT processes allow polymerization under mild conditions with spatial and temporal control. Photo-RAFT techniques enable precise patterning of polymer structures and are widely used in surface functionalization and microfabrication. PET-RAFT polymerization. Photo-induced electron transfer RAFT, PET-RAFT, polymerization employs photo-redox catalysts to generate radicals under visible light irradiation. This approach allows oxygen-tolerant polymerization and enables polymer synthesis in open systems without extensive degassing. Flow and continuous RAFT polymerization. Continuous flow reactors have been introduced to improve reaction control, heat transfer, and scalability in RAFT polymerization. These systems are increasingly used for industrial polymer synthesis. Stimuli-responsive RAFT agents. New RAFT agents capable of switchable reactivity have been developed. These agents enable the controlled polymerization of both more activated and less activated monomers, thereby facilitating the efficient synthesis of block copolymers such as poly, MAM, block poly, LAM. Surface-initiated RAFT polymerization. RAFT techniques have also been adapted for surface modification, enabling the formation of polymer brushes and functional coatings on nanoparticles, membranes, and biomedical devices. Applications of RAFT-synthesized polymers. The precise control offered by RAFT polymerization has enabled applications across numerous fields, including advanced coatings and adhesives, dispersants and surfactants, drug delivery systems, responsive hydrogels, polymer electrolytes, nanostructured materials, and membrane and filtration technologies. RAFT polymers are particularly valuable in biomedical and nanotechnology applications where controlled architecture and functionality are essential. Conclusion. RAFT polymerization is a powerful controlled radical polymerization technique that enables the synthesis of polymers with precisely defined molecular weights, narrow dispersity, and complex architectures. The mechanism relies on a reversible addition fragmentation chain transfer equilibrium mediated by thiocarbonyl Thio chain transfer agents. Proper selection of RAFT agents and reaction conditions allows control over a broad range of monomers and polymerization environments. Recent innovations such as photo-RAFT polymerization, PET-RAFT processes, continuous flow systems, and stimuli-responsive RAFT agents have further expanded the scope of this method. As a result, RAFT polymerization continues to play a central role in modern polymer chemistry and advanced materials development.